Today we have two goals. First, we want to walk through some terminology, and we're going to feel a lot of deja vu. It's like, wow, this feels like what we've talked about before. Because it is. It's just saying, let's take ideas from our previous setting to our new setting. The second thing we're going to talk about is how we start solving some of these systems of differential equations in a very special case. If you like, the constant coefficient case. So let's get going. So we're in the situation where we're dealing with differential equations and matrices. Namely, if we have something in the form x prime equals a of tx plus f of t. Now this is shorthand. So what we're doing is we're sort of putting our equations in our system together in a compact manner. So we could have written this a little bit larger, x1 prime, x2 prime, and this is what we call our x prime. It's equal to a of t, and these are our coefficients in our system, and these can be functions of t, but of course, we'll see, the simpler you make things, the better. So here's our a of t, and then we have our x1, x2, this is our x, and maybe we have some things on the end. f1 of t, whoops, excuse me, and f2 of t. All right, and here is our f of t. So again, x prime equals a of t, x plus f of t corresponds to that. Now we can write this in another way. Isn't that great? How many ways we can write things? So what do I mean by that? Well, we could, if we just think about what's happening on the top, this really is a system. And it's the top equation, x1 prime equals, you carry out the multiplication, a11 of t, x1, plus a12 of t, x2, plus our f1 of t. Then our bottom equation, x2 prime is a21 of t, x1 plus a22 of t, x2 plus f2 of t. And it's good to be able to go back and forth. So in other words, if we start with a system of two equations, can we put it into something where it's sort of more matrix slash vector form? And vice versa, can we sort of unravel? All right, well, let's start with some key ideas. Homogeneous and superposition. Well, first off, what does homogeneous mean? Now, normally, if we think back to, our differential equation setting, we said, oh, homogeneous meant there was sort of nothing on the right-hand side, right? It was zero, non-zero. But another way you could think of it says, well, all our terms were attached to what we were trying to find. In that case, maybe, if we were saying that we had a differential equation in terms of y, everything had a y attached to it, and there was equals 0, so that there was no equals 2t or e to t or anything. So the homogeneous, non-homogeneous comes down to this piece. So to be homogeneous says there's no extra stuff that isn't attached to our functions we're solving for. So non-homogeneous says, well, there is stuff that's not attached to our functions. See, x1, x2, those are what we're trying to solve for. Okay, so it's as simple as, non-homogeneous, homogeneous, non-homogeneous, homogeneous. All right, good. So why do we like homogeneous? Well, for the same reasons that we liked homogeneous before. In other words, they're well behaved. And how so? Well, it comes down to a nice fact about matrices. And in particular, when we have a matrix times a vector, well, it turns out that there's this beautiful property. So if I have a matrix A, scalar x, x is a vector, scalar y, so y is vector. So C and D are numbers, x and y are vectors. Then this is the same as, well, we're linear, which means we work well with addition, we work well with scalars. So it's the same as C, AX and d ay. So this side acts linear. The derivative acts linear, which means that both sides behave well with respect to addition and multiplying by a scalar. Which means that if we have solutions, we can make new solutions as long as we do addition and multiplying by scalar, which is superposition. So we have our nice fact. If we have some solutions, we can make more solutions by combining them in some nice way. All right, well, that's good to know. And then one of the things we said before was actually this can get all the solutions as long as we have a good collection. Okay, so what do we mean by that? Well, what we mean is we want a good collection. We want them to be linearly independent. Okay, what is that? Well, linearly independent is just a fancy way of saying everything gives you something new. So in other words, there's no redundancy. Everything builds and gives you something you weren't able to get before. So how do you check to see that you have a nice collection? Well, before we would use the Wronskian. And now we're going to use the Wronskian, just done in a slightly different way. So how does our new Wronskian work? Well, our new Wronskian works by taking a determinant. Yeah, I know that sounds a lot like before, but here's the difference. So the difference is now what do our entries look like? Well, it's the first column is solution 1. Our second column, solution 2, and so forth and so on. So in other words, we're packing the columns with solutions. This is a little bit different than before, because remember, the previous Wronskian was, functions in the first row, derivative in the next row, second derivative in the next row, and so forth and so on. So why does this work? Or another way to say, why are we doing this in this way? Well, it comes down to understanding what the Wronskian is kind of measuring. There's a way to think about it, and namely it says, can we solve any set of initial conditions? And ultimately that's what it boils down to. And that's true in both cases, for what we did before and what we're doing now. So before, our initial conditions looked like, well, you have the function at a point and the derivative at a point, and maybe more terms if we had a higher order system. So that's why we looked at functions and derivatives and so forth. Now our initial conditions, they look like, okay, at our point, we're at a certain place. Our vector satisfies a certain relationship. So we say, okay, so what we need to do is make sure we can get that vector by combining all the other vectors. So that's what's going on. All right, so that's great. So now we know how to take the Wronskian, and same as before. Non-zero, good news. Zero, things break down. So if you're always zero, hopeless. If you're sometimes zero, then you're good up till you hit that, and then you say, look, all bets are off after that point. So that's our idea. All right, so far, pretty manageable. What else? Well, as you would think, say, well, okay, suppose we have this beautiful collection of functions. We have a system of n equations. We have n as linearly independent solutions. No, don't get nervous when we say n equations. Usually we're talking n equals 2. That's going to be, if we can get that, we'll be happy. Now what we say is, great, superposition, that gets all the solutions. So every solution is some combination of these base solutions. So we again reduce to saying, can we find our small number of solutions, which are all distinct, then we get all of them. And if you think about what we're talking about, we're still in our homogeneous setting. So we could say another way to think about what we have here is that this is our XC, our complementary solution, right? So complementary solution being that we solve the homogeneous part. Well, what if we have something non-homogeneous? Well, that could happen, but don't worry, we have ways to handle that. So remember, what do? For non-homogeneous, say, look, find a solution. So if we have a non-homogeneous part, so we have some f of t, then we find one solution. We call that our particular solution, xp of t. And then what do we say? Well, look, all solutions are found by taking the one we had, our xc, and adding xp. And so that gets everything. So the way to think about it, as before, xp has a job. The job for xp is to say, hey, I can handle the fact that it's non-homogeneous. I got that f of t covered. And then the xc says, oh, great, that's cool. What I'll do is I'll make sure we can get all the initial conditions satisfied. And we're like, yeah, our powers combined, we got this. And they do. The last thing to talk about is, what if we have initial conditions? So what do initial conditions look like? Well, they say that at some time, a, our initial starting place, x of a, is equal to b. It's a vector. You say, okay, well, how do you find that? Well, what you really have to find are what are the right c's. So you plug in a into all the pieces, and then you say, all right, that gives you an equation to solve for in terms of c's. But they're nice equations, in particular linear equations. And we know how to solve linear equations. Like 2 equations, 2 unknowns, 3 equations, 3 unknowns. We can talk about substitution. We can talk about elimination. We can even pull in matrix tools. But at the end of the day, we do have the technology to help solve for our initial conditions. All right, great. So same ideas as before, just slightly new setting, but that means we're ready to delve in and try some of these things out. So let's try all of the things we just talked about with the following example. So consider the linear ODE system. X prime equals, we have our matrix here, t to the negative 1, t squared, 4t to the negative 4, t to the negative 1, x. So this is our a of t, x, minus 6, 0, t to the negative 1. So this is our f of t. And so notice we've pulled out a 6, and that's okay. We might say, wait, weren't we supposed to add? It's all right. Subtraction, addition, potato, potato. We're fine. It's all good. Okay. Well, there's a lot of steps here for us. So let's start with the beginning. Verify that x1, which is this function t to the 5th 4t squared, and x2, which is minus 1t to the negative 3, are solutions to the homogeneous system. Well, what's the homogeneous system? Well, the homogeneous system says we don't want any f of t. So for this part, we say, all right, we really want x prime equals t to the negative 1, 4t to negative 4, t squared, t to the negative 1, x. So this is our homogeneous system. Okay. Well, all right, how do we verify something? Okay, well, we just sort of put on our hat saying, we heard the word verify before, and what did it mean? It meant plug it in. So we're going to plug it in, and we'll see what happens. So we just have to plug it in to both sides. And then, if when we plug in on the left, we get the same thing when we plug in on the right, life is good. So, well, a bit of work ahead of us. So let's start with our x1. So we have our x prime. Well, that says what? Well, we're going to take the derivative. So how do you take the derivative? Well, you do it entry-wise. So derivative of t to the 5th, 5t to the 4th. Derivative of 4t squared is 8t. Good. Now, that's the left-hand side. On the right-hand side, we have our t negative 1, 4t to negative 4, t squared, t to negative 1. And I'll go ahead and write this down here. T to the 5th, 4t squared. Okay, time for us to practice our matrix multiplication. So, along the first row, down the column. Here we go. T to the minus 1 times t to the 5th gives us t to the 4th. T squared times 4t squared gives us 4t to the 4th. All right, going to the second row. So second row, and then down the column. 4t to the minus 4 times t to the 5 gives us 4t. T to the minus 1 times 4t squared gives us another 4t. Well, we add those together, and we'll get 5t to the 4th in the first entry, and 8t in the second entry. And now we look at this and say, do they match? And they do. They're the same. Woohoo! All right. So, since they match, that tells us x1 is a solution. Okay, so we've done the verification for x1. Now, we have to do the same thing for x2. All right, so similar process. Here we go, x2. We have x prime. Well, the derivative of negative 1 is 0. Derivative of t to the negative 3 minus 3t to the negative 4, right? We're going to subtract 1. That's how derivative rule works. Okay, and now we're going to multiply t to the negative 1, t squared, 4t to the negative 4, t to the negative 1 times, negative 1, and t to the negative 3. Got to keep track of which one we're working on. All right, so again, first row down the column. T to the negative 1 times negative 1 is minus t to the negative 1. T squared times t to the negative 3 would be a positive t to the negative 1. Now second row down the column. 4t to the negative 4 times negative 1 minus 4t to the negative 4. Then t to the minus 1 times t to the minus 3 is t to the minus 4. Well, minus t to the minus 1 plus t to the minus 1 gives us a grand total of nothing. They cancel. Well, we kind of expected it to. All right, minus 4t to the minus 4 plus t to the minus 4 would give us minus 3t to the minus 4. And now we say, aha, do they match? And they do. And so we are happy. Yes. So that takes care of x2. And so we verified. So now we have that both of these are solutions. Woohoo! Yeah! All right, on to the next part. Verify that x1 and x2 are linearly independent using the Wronskian. So we say, all right, we know how to handle the Wronskian. We just talked about it. We take our two functions, x1, x2, and we're going to make a matrix. So the first column will be x1. So we say, okay, so that's our t to the 5th, 4t squared. The second column is our x2. So that's minus 1t to the minus 3. All right, t to the 5th times t to the minus 3 would give us t squared. Down the diagonal. Subtract, going up the diagonal, 4t squared times minus 1 is minus 4t squared. Well, that's 5t squared, and that's not 0. And they might say, oh, well, wait. Steve, you have a problem at 0. Oh, yes, we definitely have a problem at 0. 0 is actually a big problem because what happens? This isn't even defined. And the matrix also is not defined. So yeah, we already knew that 0 was a problem. So we're saying, all right, away from 0, life is good. We're linearly independent. We can always find our solutions as long as we try something not at t equals 0. All right, great. Well, more progress. We've just finished the second part. Good. Now, write the general form for our xc. And that sounds like it would be hard, but actually we can build off of what we've done. Why? Because what have we done? Well, we took these two, x1, x2, we verified that they're both solutions. We verified that they're linearly independent, which means that they're each giving us something new. So what we can do now is superposition gives us all solutions. So we could say, aha, our xc looks like some constant, and I'll use c, times the first function, and our first function is t to the fifth, 4t squared, plus some constant, again working through the alphabet, d, times our second function, minus 1 t to the minus 3. And there we go. There we go. Good. Ah, we're picking up speed. We're halfway done. But another way to look at it, we have half to go. Well, yes, both those statements are true at the same time. We need more paper, but don't worry. We have more paper, as we say. Lots of paper out there. Okay. So, where are we at? Well, now we're to verifying for xp. So in some sense, we got xc. Now we have to handle the particular solution, which means we're bringing back this piece here. So what do we do to verify? Well, previously when we wanted to verify it, we plugged it in. Now when we want to verify, we're going to plug it in. So that's, whenever you see verify, you're just like, oh, do you mean plug it in? Yeah, that's exactly what we mean. Okay, great, cool. So we're going to plug it into both sides. So on the left-hand side, we're going to look at xp prime. Okay, so what would that be? Well, derivative of t cubed is 3t squared, and the derivative of 2 is 0. Okay, good. Now we're going to plug it into the other side. It's a little bit more action-packed. All right, so we have t to negative 1, t squared, 4t to negative 4, t to negative 1, times our xp, t cubed 2, minus 6, 0, t to negative 1. All right, so let's first carry out this matrix multiplication. So again, first row down the column. T to the minus 1 times t cubed will give us t squared. All right, well, that's good. T squared times 2, 2t squared. All right, now second row down the column. 4t to the minus 4 times t cubed would be 4t to the minus 1. T to the minus 1 times 2 will give us 2t to the minus 1. Subtract 6, 0, t to the minus 1. Now, we can just combine the top entries, right? So we have t squared plus 2t squared minus 6 times 0. So what does that give us? T squared plus 2t squared minus 6 times 0 gives us 3t squared. Good. Bottom, 4t to the minus 1 plus 2t to the minus 1, that's 6t to the minus 1. We're going to subtract 6t to the minus 1. Well, 6t to the minus 1, subtract 6t to the minus 1, gives us 0. Nice. And so we have that. All right. And now we plugged it into the left-hand side. We plugged it into the right-hand side. And what do? We check. Do they match? And they do. So woohoo! So matching is good. It's just like socks. You always want them to match up. All right. So now we have our particular solution. So we've done that. Two things left. Write the general form for our solution to this differential equation. Okay, so what will that look like? Well, remember our general form looks like x is our particular solution, xp, plus our xc. It doesn't matter which order you put them in. So that looks like our xp, t cubed 2, and then our xc, remember it was combinations of x1, x2. So it's some constant, x1, and plus some constant, x2. All right, and there's our general form. Nice. And one more thing to go, and then we'll be done. Find the solution satisfying x of 1 equals 6, 7. Well, let's give ourselves some more space. So I'm going to just turn this piece of paper over. And here we go. Okay, so quickly we'll rewrite what is our x. Our x looked like our particular solution, t cubed 2 plus some constant c, t to the 5th, 4t squared, plus some constant d, minus 1, t to the minus 3. Okay, so there's x. So now we're ready. So we're going to plug in 1, and we want to get out 6, 7. So x of 1, well, we should get 6, 7. That should equal 1, 2, because right, everywhere where you see a t, you put a 1. So 1, 2, plus c, 1, 4. 1 is a very nice number when you're trying to evaluate 1 to a power. It's just always 1. And then plus d, minus 1, 1. Okay, now when you look at this, you can actually think about just reading off the two equations. So you might say, wait, wow, where are there two equations? It kind of looks like one equation. But when I say two equations, I mean the top entries, the bottom entries. So let's read off the top entries. What do we have? Well, we have 6 equals 1 plus c minus d. Or we could say c minus d is equal to 5. Bottom row. 7 is equal to 2 plus 4c and then plus d. Or, again, we can move the 2 across. 4 times c plus d is equal to, again, 5. And now we have two equations, two unknowns. Life is good. We're in our happy state. We can even say, aha, adding cancels off the d's. What? That was so kind of them. Yes, our instructors are kind, loving people. So c should be 2. Well, now that you know c is 2, you can say plug into the first equation, and you'll get 2 minus d equals 5. And then that tells us that d is negative 3. So, our answer. What is the solution? Well, it is x is t cubed 2 plus 2, because c is 2, times t to the 5th, 4t squared, and then minus 3 minus 1 t to the minus 3. And that's perfectly fine. And since it's perfectly fine, I'll box it. The other thing you can do is you can also put them all together into a single vector. And so if we did that, what would we have? Well, we'd have t cubed, and then plus 2t to the 5th, and then minus 3 times minus 1 plus 3. Then the other one, we'd have 2. 2 times 4 makes 8. T squared. And minus 3 t to the minus 3. And so that's the other way to write it. Both are great. It's not that one is preferable to the other. It just is a matter of taste and what you're trying to do. Oftentimes, if you're trying to get it down to a system, sometimes you put things into a matrix, and then at the end you want to pull out of a matrix, and it's a little bit nice when it's of this form, but with practice, everything works pretty well. All right, so that's been a great exercise for all our ideas. So in the example we just went through, we were given our solutions x1, x2, which is nice, but can we ever solve it by ourselves? In other words, are there cases where we can explicitly find them? And the answer is yes. Now, how do we get there? Well, we just keep simplifying, simplifying, simplifying. So we're going to make two simplifying assumptions. The first one is let's make it homogeneous, because that makes life easier. Now, I know you're worried, like, but I love non-homogeneous. Just wait, we'll get to that. But again, simplify first. The other thing we're going to talk about is constant coefficient. So when we're thinking about our constant coefficient, that's coming into what our matrix A looked like. So previously, A, we said, well, it could be functions of t, and that's what we saw in the previous example. But now we're going to say, well, look, A won't depend on t anymore. A is just a bunch of numbers, constants. Okay, so now if we've simplified this far, we can make progress. So let's think about what we were doing. And the suggestion here, constant coefficient, is very like ringing some bells for us. It's just like, hey, we had an idea. And in that case, we said, well, let's pick our favorite function. For differential equations, our favorite function, exponential. And so we said, well, let's make things look like an exponential and try it out. So we would plug in e to the rt. That would lead us to a characteristic equation, which in other words, a polynomial only involving r, and then we'd have to figure out what r is. So it was turning it into an algebra problem. But the key here is we guessed exponential. So if it worked once, why not have it work again? So we want to guess exponential. All right, well, what will our solution look like? So we're going to guess, again, e to something t. But we can't just have that. See, the problem is we're dealing with a system. We have multiple equations. So we're going to have something in front. So here, we're going to add a vector v. So there's a vector v, and then there's this e to the lambda t. Now v is a vector which is constant. There are numbers here. So you can, roughly speaking, think of it as a function times a constant. It's not a bad way to think about it. So here we go. What do? We're going to plug it in. So now we say, all right, we're starting with x prime equals ax. Our guess is e to lambda t times v. Well, plug it into the left-hand side. Well, since the v acts like a constant, the only thing that's changing is the e to the lambda t. So the derivative would be lambda, because that comes down, e to the lambda t times v. And on the other hand, a times x, well, just a times x. And we're like, wow, that looks cool. We can cancel the e to the lambda t's. So we've transformed our problem and said, okay, so now what we're looking for is we're looking for something where this is true, where a times v equals lambda times v. Now, what's cool about this? Well, notice what's not here. There's no derivatives in sight. So we've removed derivatives from the problem. So what does that tell us? Well, we've transformed the problem into a different kind of problem. And so in particular, this is a linear algebra problem. So linear algebra is the study of matrices and their properties. And so now we have to say, okay, so our goal is, can we find values lambda and vectors v so that a times v is lambda times v? Has it been studied? Does it have names? And yes, it has been studied. And yes, it does have a name. So we're really interested in what are known as eigenvalues, eigenvectors. Now, eigen, that's kind of a weird word. It's German. And roughly speaking, it more or less means same. Now, you might say, well, how is this the same vector? So what are we after? Well, we're after A times vector V, and the output looks a lot like V. So that's why we call it the same vector. It says, oh, when you multiply the vector, you get basically the same vector back, except you may have to scale it. So what we have is that lambda is our eigenvalue, and V is our eigenvector. All right, so how do we go about finding eigenvalues and eigenvectors? Let's start with the eigenvalue part. So what do we have? Well, we know we have that lambda times V is A times V. We're going to move things around. So that says the zero vector is AB subtract lambda V, because we can move things around. It does work just like we think addition should work. And now what we want to do is we want to pull out the V. And we say, well, that should be easy, right? If you see AV minus lambda V, wouldn't that just be A minus lambda times V? Well, one small problem. This part is nonsense. It means nothing. Nothing. It doesn't make sense to talk about a matrix and you subtract off a number. But that's okay. We can fix it. This is a fixable problem. And how do you fix it? Well, we say, look, let's add a little piece here. And so we say, okay, what's this? I. It's our 1. Multiplying by the identity is like multiplying by 1. And so then we can pull it out. And when we do that, will be A minus lambda I times V equals 0. Now, it turns out that if this is the case, that I have a matrix times a non-zero vector, and I get 0 out, something has to sort of be wrong with this matrix. Matrices normally only have this relationship if V is a 0 vector. So what's wrong? Well, there's lots of things that are wrong, but the simplest thing for us is to say, if you look at the determinant of this matrix, so that's what the bars mean, that's the determinant, it must be 0. All right, so here we go. When we want eigenvalues, we want the determinant of A minus lambda I to be 0. So saying it one more time, when we're finding eigenvalues for a matrix A, we take the determinant of A minus lambda I. Now, this is a polynomial. It's a polynomial in lambda, and we say set that polynomial to 0. Now, this polynomial has a name. We call it the characteristic polynomial. And I might say characteristic polynomial. We've seen things like that before. Yes. Yes. Is that a coincidence? No. No. It's not a coincidence. Okay, so let's find the eigenvalues for this 2 by 2 matrix. So here we go. What do we do? Well, this right here is our matrix A. So we're going to look at A minus lambda I. Now, since we're just starting out, let's do this a little bit slowly. Remember, when we talk about I, this is 1, 0, 0, 1. So when we talk about A minus lambda I, this would be 4 minus 3, 6 minus 7. I'm just copying down what A is. And then subtract lambda, 1, 0, 0, 1. And now, just entry by entry. That would be 4 minus lambda, then minus 3 minus 0, and then 6 minus 0, and then minus 7 minus lambda. All right, so the punchline here is you subtract lambda off the diagonals. Oftentimes we'll go straight here, but the first time we see it, we just want to go slowly. But okay, again, subtracting lambda I means subtract lambda on the diagonal terms. So now what comes next? Well, the next thing is to take the determinant. So we're going to take the determinant of 4 minus lambda minus 3, 6, minus 7 minus lambda. All right, so this will be, and I probably should have given myself more space. I'm already regretting it, but that's all right. Down the diagonal, 4 minus lambda minus 7 minus lambda, subtract 6 times negative 3. Okay, so expand. 4 times 7 is 28. Oh, 4 times negative 7, negative 28. Make sure you're careful. Minus 4 times minus lambda, minus 4 lambda, minus lambda times minus 7, plus 7 lambda, and minus lambda times minus lambda is plus lambda squared. And we have minus 6 times minus 3, that's minus a negative 18, which makes a plus 18, which becomes lambda squared, then 7 lambda minus 4 lambda, plus 3 lambda, and minus 10. And remember, we set this equal to 0. All right. Well, we can either factor, or we can use quadratic formula, or maybe complete the square, but probably try factoring first. If it factors, do it. Does it factor? Well, maybe. What do we need? Two numbers that multiply together to give us negative 10, but when we add, we get positive 3. Yeah, we can find numbers like that, namely plus 5 and minus 2. Let's double check, right? We should always check our work. Lambda squared, that's good. Minus 2 lambda plus 5 lambda is plus 3 lambda, and minus 2 times 5 is minus 10. So that leads us to our wonderful conclusion that our eigenvalues are negative 5, positive 2. Good, good. Now, there's a tip here that says you can actually check a couple things. And that is to say, if you add these together, negative 5 plus 2 is what? It's negative 3. That's the same as the sum on the diagonal. Well, 4 plus negative 7, negative 3. Coincidence? No, it's not a coincidence. You can also, if you multiply these, you get negative 10. And now take the determinant. Minus 28, subtract minus 18 is negative 10. Another coincidence? No. So there's some small checks you can do. And of course, the most important thing is don't rush. Take your time. You'll be fine. Now, before we get to the eigenvectors, and we will, don't worry, I want to take a moment to look at this. Use the method of elimination, which is a variant of Cramer's rule, on the system x1 prime equals 4x1 minus 3x2, and x2 prime is 6x1 minus 7x2, and find the roots of the corresponding characteristic polynomial. All right, now, does this look familiar? And I want to pull out the previous problem. I happen to have it here. And if you look at the coefficients, you'll see you'll have 4 minus 3, 6 minus 7. So there is a connection to these numbers. So this actually connects back to the previous problem. And I want to see what happens. And in particular, say, hey, is something similar happening? So what goes on? Well, we move everything over to one side, x1 prime minus 4x1 plus 3x2 is equal to 0. And then we'll have minus 6x1 plus x2 prime plus 7x2 equals 0. All right, good. Now, for reasons which are going to hopefully make sense in just a moment, I'm actually going to multiply everything through by a negative on both rows. And there's not really a good reason why to do it now, but it will help us to see something in just a second here. All right, so I'm going to think of this as here, we can rewrite this as 4x1 minus x1 prime minus 3x2 equals 0. And here we'll have 6x1, and then we'll have minus 7x2 minus x2 prime equals 0. Now, keep going using our d notation. So here we'd have 4 minus d x1, and then we'd have minus 3. I'll go ahead and put this as a plus, a minus 3x2, and then we'd have a 6 x1, then a plus minus 7 minus d x2. All right. Now, put it into a determinant. Let's say we just want to find x1. It won't matter whether we're looking for x1 or x2. We'll end up getting the same thing in terms of what determinant we're after. So we have the determinant of 4 minus d minus 3, 6 minus 7 minus d, x1 equals, well, on this other side you replace the first column, which is the x1 column, by all zeros. But the thing is, because you have all zeros in a column, that will become 0. Okay, now pause here before we go much further and say, hey, look here, 4 minus d, 3, 6, minus 7 minus d, and we're taking this determinant. That looks an awful lot like what we have here. 4 minus lambda, minus 3, 6, minus 7 minus lambda, and we're taking the determinant. Coincidence? No, it's not a coincidence. It's not a coincidence at all. All right, so, well, from here, you'll see a lot of deja vu. So we're going to take 4 minus d times minus 7 minus d, subtract 6 times negative 3 times x1 equals 0. And, okay, so that's minus 28 minus 4d plus 7d plus d squared, and then plus 18 times x1 equals 0, which becomes d squared plus 3d minus 10 times x1 equals 0, which leads us to the equation x1 double prime plus 3x1 prime minus 10x1 equals 0. Now, again, come back and say, hey, we have our 4 minus lambda minus 7 minus lambda, subtract 6 times negative 3. It's the same thing. We're getting down to lambda squared plus 3 lambda minus 10, which, if you look, what's going to happen is the characteristic polynomial, that's r squared plus 3r minus 10. And we know what's happening. It gives us our same value for r that we've already found, namely r is negative 5 and positive 2. So in other words, you can think about what's going on here about finding the eigenvalues. It's a similar thing about what's happening with the Cramer's rule, but now it's just we have it in a different setting. So it's nothing too crazy. It actually fits in with what we've already done. Isn't it nice when things fit together? Yeah, I think it's great. So we talked about finding eigenvalues. We also need to talk about finding eigenvectors. Okay, so let's suppose we have our matrix A and we've already succeeded in finding our eigenvalue lambda. How do we find the eigenvector, or possibly eigenvectors, it could happen, that go along with it? Well, we are trying to set up our equation. A minus lambda I, here I put a y, but you can think of it as your v, equals 0. And now we're saying we want to solve that. All right, well, what can we do? It sounds like it could take a while, but actually it's surprisingly easy. For the 2 by 2 case, it's free. You don't even have to put a lot of thought into it. You do have to put some practice to get used to it. So here's the thing. If we have a 2 by 2, then what we do is we write the matrix A minus lambda I, and that will lead us to a matrix with some entries. So remember, lambda at this point is a number, so there's no unknowns. Everything's known. And now you say, okay, I have this. I have alpha, beta, gamma, delta times something, and I need to get to 0, 0. So the goal is, what's in the vector? What goes here that works? As long as you can find one thing that works, life is good. So what you can do is you can say, I can use advantage of the fact that I know things are sort of breaking down. Say, look, as long as I can get something knocking out the row, it should knock out the other row simultaneously. So what can you do? Well, the claim is, look, pick a row. Doesn't matter which row. Write it backwards. So I'll write beta alpha. And now flip a sign. This will work. And why? Well, look, alpha beta minus alpha beta is 0. Now you might say, well, great, but what about the second row? Okay, so here's the cool thing. When we have that the determinant is 0 for a matrix, 2 by 2 matrix, it turns out that the second row looks like the top row. It's just a multiple of it. And so, since it's a multiple, if it works for the top, it works for the bottom. So, this is great. It says you can fill it in really quickly. Now, I know that's really, right now it's very like, too many symbols. We'll do an example and drive it home. And then we're going to do example after example after example over the next few lectures. And you're going to be like, okay, I got this. There's one more pro tip here, which we should point out. And that is to say, hey, if you have an eigenvector, you can scale it. And so in particular, say all the entries are negative. Great, multiply by negative. All the entries are positive. Or maybe everything has a factor of 2. Great, pull out the factor of 2. Or maybe there's fractions. Okay, multiply in and get rid of the fractions. You've got options. So you can really make your eigenvectors very pretty. And we'll see why that works out so nicely in our next example. So our final example for today. Here we have a matrix A, 4, minus 3, 6, minus 7. Use the eigenvalues previously found. So in fact, this is the same matrix that we found before. So we know our eigenvalues are negative 5 and positive 2. All right. Use that to find the eigenvectors. Okay, so that's find the eigenvectors. After we found the eigenvectors, we're going to give the general form for solutions for x prime equals ax. So let's first focus on eigenvectors. So how does that work? Well, you have 2 eigenvalues. For each eigenvalue, we're going to look for eigenvectors. So let's start with the negative 5. And there's not a, start with this one first versus start with that one. You just pick one. And now look at A minus lambda I. Well, in this case, that's a, lambda is negative 5, so that's plus 5i. And so this says add 5 to your diagonal terms. So we're going to get 9 minus 3 and 6 minus 2. Okay, so what we're doing here is we want to find our eigenvector is something where we get 0, 0. So we just need to find one thing that works. So let's talk about our method we just sort of walked through. It says, hey, pick a row. Okay, I picked this row. Now, write the entries backwards. Negative 3, 9. Flip the sign of one of the entries. I could flip the sign of that entry. And now you're done. There's your eigenvector. So negative 3, negative 9. So you have negative 27 plus 27. Yeah, that's 0. Minus 18 plus 18. That's 0. All right. So that was quick, right? So you might say, okay, do I have to use negative 3, negative 9? Well, no. We can scale it by any amount. So I could choose 3, 9. Or, hey, everything's divisible by 3, 1, 3. Or, of course, there's many options. The only thing is not 0, 0. 0, 0, boring. Not going to work. Okay. Second eigenvector. So here we go. Now we'll do lambda equals plus 2. Okay, so we're looking at a minus lambda I. That's a minus 2i. So we're going to subtract 2 off the diagonal terms. So that's 2 minus 3, 6 minus 9. All right, so like before, we have our matrix here. We're looking for some vector. What vector can we put here so that this is true? So, okay, pick a row. I always like to pick the easiest row. And if they both look equally easy, all right, then I'll pick the first row. Then, okay, I see 2, negative 3. So write it backwards. Negative 3, 2. Flip the sign of one of the entries. Okay, I'll make it positive 3, 2. And done. Check, right? 6 minus 6, 0. 18 minus 18, 0. And life is good. So yeah, so we can use 3, 2. Or we could use negative 3, negative 2. Or we could choose 300, 200, or lots of choices. What's the right choice? The right choice is the simple choice. Make things easy to work with. Because at some point, we're going to work with these things, and we want them to be something that we can handle. Okay, so we found our eigenvectors. They're not unique, but up to scaling, they are unique. Whew! Now, ready for the second part. Use this to give the general form for solutions of x prime equals ax. Now, this comes back to what we were talking about. What do solutions look like? Well, solutions, they look like our e to the lambda t times v, where, what do we have? Well, lambda is eigenvalue, v is eigenvector. So, say, okay, great. We have eigenvalue with eigenvector, eigenvalue with eigenvector. So, we have two solutions. Namely, we can choose e to the minus 5t times 1, 3. And we also have e to the 2t, so 2, 2, times 3, 2. Here are our two solutions. Well, what can we do? It's linear, it's homogeneous. We can do superposition. Yes, superposition. So that's what we're going to do. We'll superposition these together. Say x looks like some constant c times our first solution plus some constant d times our second. And that's our answer. Now, I said, why don't we care about which one we use? Well, how do they differ? They differ by a constant scaling factor, right? And notice, what do we have here? A constant scaling factor. So that's why if I had written down a 3, 9, I could pull a 3 out and it would get absorbed into the constant here. Same thing on this side. It gets absorbed into the constant. So that's why really we handle all possibilities because of these constant scaling factors. Isn't that great how everything fits together? It's almost like it was meant to be. A match made in mathematical heaven. That's it for now. It's been a lot today, a lot to think about. Don't worry, we'll get more practice in the next few lectures. All right, take care. Bye.